Hi, AP class. This is Mr. Mellinger, and this is your lesson on chemical bonds. So, a chemical bond is when two or more atoms are attracted to each other. So, there's 92 elements in the universe that are able to form tens and tens of millions of substances, even hundreds and hundreds of thousands in your body. And when those atoms are joined together, there's only three different ways that they're able to do that. So chemical bonds can be between atoms of the same element, such as two oxygen atoms to form O2, which is an oxygen molecule. That's what we actually breathe in. Or different elements, such as H2O. That would be two hydrogens and an oxygen, and that's called a compound. When the elements are different and they bond, they are called compounds. It's because of chemical bonds that elements on the periodic table can form all the different substances in the universe. So there's three major types of chemical bonds. And again, that's such an amazing fact that everything in the universe is created because these atoms join together, and there's only three different ways that they do it. It's really, really amazing. One is covalent bonds, the second is ionic bonds, and the third is metallic bonds. Now look at your periodic table. The nonmetals are those elements to the right-hand side of the periodic table. And covalent bonds are formed when two nonmetals bond together. Ionic bonds are formed when nonmetals are bonded to metals, and metals are everything on the left-hand side of the periodic table, everything from that stair step all the way to the left, and then that's an ionic bond. So it's a nonmetal to a metal. And then the third type of bond, which we don't talk about and deal with quite as much in chemistry, is metallic bonds. And those are bonds between metal atoms. It may be the same metal, it may be just pure copper, and the bonds are formed between copper atoms, or it could be between two different metals. So let's start with covalent bonds. What are covalent bonds? Covalent bonds occur when two or more atoms share electrons. That's the key word to remember with covalent bonds is sharing. Covalent bonds are the bonds that are found in you and other living organisms. So covalent bonds occur primarily between nonmetals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, chlorine, and the others. Covalent bonds produce combinations of atoms called molecules. And we'll talk more about molecules. We'll talk about them quite a bit, actually. So remember that covalent bonds share. So what is a Lewis dot structure? This is a little bit of a digression from the subject, but we are going to study bonds and a lot of very sophisticated facts you can be determined about bonds by drawing Lewis dot structures, even though they seem very simplistic. So Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. That's it. So this is a diagram of a beryllium atom. It's drawn the way that you learn to draw the diagram. And so to do the Lewis dot structure for beryllium, you first write the atomic symbol, Be, and then you take the two valence electrons as you see them there, and you draw only the valence electrons around the atomic symbol. So there goes that valence electron and then the second one, and that's the Lewis dot structure for beryllium. We're not concerned about the core electrons. They don't get involved in chemical bonding. It is only the valence electrons, those on the outer shell, that get involved in chemical bonds. So Lewis dot structures show only valence electrons, since only these electrons are involved in chemical bonds. Here's just another example of oxygen. So we're going to write the atomic symbol O, and then we're going to draw only the valence electrons around the symbol O. And the reason I had you draw valence electrons the way I did, where you went around the circle and then started pairing them up, is exactly so that you could translate that directly into the Lewis dot structure, and that's what you see there for oxygen. Here's one for phosphorus. Write the atomic symbol, And you can see the valence electrons there. So we're going to draw only those valence electrons, and there they go. Now the key here, for oxygen there were 2 unpaired electrons. For phosphorus there's 3 unpaired electrons. Those are the ones that are going to form covalent bonds with the unpaired electrons in other atoms, as you'll see in just a moment. So what is the octet rule? The octet rule is one of the fundamental rules of chemistry, and it's one of those magical kind of rules that you ask, why does it happen? Right now, we're not going to worry about so much why the octet rule works. We'll get into some of the physical explanations of why it works so that you can describe those for the advanced placement exam. But just even if it just seems like magic, just understand that it does exist, and it's how you determine whether a bond will take place or won't take place. So the octet rule says that atoms are happy when they can fill their valence orbital. So atoms like to have their outer orbital filled. Octet means 8. It's called the octet because elements in the second and third periods and below need 8 electrons to fill their valence orbital. So here's an example of an oxygen. It has 8 protons, 8 electrons, 8 neutrons. So you can see its valence orbital has 6 electrons. It would really like to add electrons to those 2 additional spaces. And it's that desire to have those electrons come in there that creates the octet rule. Now, we have to watch out for using terms like happy and want to have a desire to have the electrons come. Remember, atoms are not people. They don't think. So you have to watch out for those explanations when you get to the AP exam. But for right now, while we're just learning the basic concepts, it's okay to use terms like that. And we'll eventually get past that. Okay, so what is the octet rule? The octet rule states that atoms are happy when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second and third period rows and below actually need 8 electrons to fill their valence orbital. But what about hydrogen? Hydrogen's valence orbital can only hold 2 electrons. That's the first orbital. So hydrogen needs 1 electron to be happy to fill its valence orbital. So even though hydrogen only needs 2 electrons, it's still called octet. So octet really means full valence orbital in this case, not that there's 8 electrons. So note that even though hydrogen can hold only 2, not 8 electrons, it's called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So hydrogen has that 1 empty space, has 1 electron, so it has 1 empty space in its valence orbital. So now we're going to see something really special here. Each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 valence electrons, so oxygen is happy. So watch how these electrons of each of these elements comes together to fill the empty spaces of the other. So you have 2 hydrogens and an oxygen. And that one comes to fill that empty space on the top. And then on the right side, that hydrogen comes in to fill the empty space for oxygen. So oxygen shares an electron to fill the valence orbital of each hydrogen so that the hydrogens are happy. So let's count. If you count the shared electrons around oxygen, there's 1, 2, 3, 4, or the electrons around oxygen in the valence orbital now, there's 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And if you look at each of the hydrogens, they have 2 electrons in their valence orbital, so everybody's happy. Now you may notice you're counting some of the electrons twice. You're counting those shared electrons for both hydrogen and for the oxygen. That's okay. You're double counting them, but that's okay. So that is what's meant by covalent bonds sharing electrons. So there are the shared electrons right there. And that's the covalent bonding of a water molecule. So because 2 hydrogens fill the valence orbital of oxygen and oxygen fills the valence orbital of the 2 hydrogens, this combination creates H2O or water. So the bonds created by atoms sharing electrons according to the octet rule are called covalent bonds. Covalent bonds share electrons. The word co means together, the prefix co means together, and valent means valence, refers to valence electrons. So it means the valence electrons are together, they're shared. Okay, there's some special molecules that we're going to deal with a lot, so we'll just introduce them right now. They're called diatomic molecules. Diatomic molecule is a bond between two atoms of the same element. Technically, it could mean just that there's two atoms. That's what diatomic means, two atoms. But generally, when we speak of it, we're speaking of these specific molecules. So diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules, and you should memorize these. 4 of these are halogens with 7 valence electrons. So fluorine, chlorine, bromine, iodine, hydrogen, oxygen, and nitrogen. So in other words, when you say that we breathe oxygen, Okay, I had to take a brief pause there. So oxygen, when we breathe oxygen, we're not breathing oxygen atoms. We're breathing oxygen molecules. That's 2 oxygen atoms that are bonded together with a covalent bond. Oxygen as a gas will never exist as independent atoms. It will always bond with other oxygen atoms. And the same for the other of the diatomic molecules, including hydrogen and most of the nonmetal gases. Okay, so a diatomic molecule is a bond between 2 atoms of the same element. Diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens, so we haven't gotten into those different subcategories of the periodic table. We'll do that within the next few days. 4 of these are halogens with 7 valence electrons. And the halogens all have 7 valence electrons. That's fluorine, chlorine, bromine, iodine, and so forth. Okay, so again, here's a little animation. There's 2 fluorines. They each have 7. So I think you can guess what's going to happen here. There's an empty space on that fluorine. There's an empty space on that fluorine. And there they come together. So now if you count, each of those fluorines is surrounded by 8 electrons. It has a full valence orbital. And so therefore, that's why these diatomic molecules form very easily with halogens. So now we're going to move to the next type of bond. The next major type is an ionic bond. An ionic bond is formed between a nonmetal, the ones we were just talking about, and a metal. And that's anything else on the periodic table that's not a nonmetal. So ionic bonds result when an atom transfers an electron to another atom. So they're not sharing electrons. One atom is completely giving up its electron to another atom. The atom that lost the electron becomes positively charged, okay? Just stop and think about that. It was electrically neutral, had the same number of electrons as protons. It loses a negatively charged electron, so now it has a net positive charge. It has more protons than electrons, so it's now positively charged, and that's a cation. And the atoms that gain the electrons become negatively charged. They have one more electron than proton, and they are anions. It could be more than a single electron, by the way, but for our purposes right now, we'll say it's one electron. The positively and negatively charged atoms are then attracted to each other, just like magnets. North pole, south pole, positive, negative. Again, as I said, so much of chemistry just boils down to this attraction between positive and negative, or repulsion between positive, positive, or negative, negative. But in this case, it's an attraction between a positive cation and a negative anion. So which atoms give up electrons in ionic bonds? The atoms that give up electrons are usually alkaline metals and alkaline earth metals quite a bit, and it's really the transition metals too. Those are the metals in that low valley right in the middle of the periodic table. But for ionic bonds, it's oftentimes those on the far left-hand side. These have very low ionization energies. Remember that? And we talked about why they have low ionization energies. They have very few protons to pull their valence electrons or to hold on to their valence electrons. So they easily give up electrons. So right there, these two groups, the one on the far left is called the alkali metals, and the one that's second over that starts with beryllium and goes magnesium, calcium, the second column down, those are called alkaline earth metals. The atoms that attract the electrons are the nonmetals, because remember, they have high electronegativity. They really like to pull in an electron from the outside, and particularly the halogens in the second to last column, fluorine, chlorine, bromine, they really like to pull on electrons. These elements have high electronegativity, so they strongly attract electrons. So those elements right there that you see in green. So lithium has a low ionization energy, which means it easily gives up its second orbital electron, that one valence electron. And fluorine has high electronegativity. It has that empty space over there, so it wants to pull in an electron. So of course, what happens, we talked about this in a previous lesson, when lithium and fluorine get together, lithium gives up one of its valence electrons to fluorine. And there it goes. So what you see now is fluorine has a full outer orbital, a full octet, 8 electrons in its outer or valence orbital, so it's happy. Now look what happened to lithium. It had 1 electron in its second orbital. It gave it up, so it no longer has any electrons in its second orbital. That means that's no longer lithium's valence orbital. It's lost that as its valence orbital. So now its first orbital is its valence orbital. And you'll see that it has 2 electrons in the first orbital, and that makes it happy because the first orbital can only hold 2 electrons. So fluorine gained its octet or fulfilled the octet rule by adding an electron, and lithium fulfilled the octet rule by subtraction, by getting rid of an electron and then losing its second orbital because there was nothing there. So now its first orbital is its valence orbital. Okay, so now lithium has a positive charge because you see it has 3 protons and only 2 electrons. Lithium is a positively charged cation, positive cat, because it has 1 more proton than electron. Fluorine is a negatively charged anion, negative ant, because it has 1 more electron than proton. So positive, negative, very first slide we had in this class, they attract each other, and that's called an ionic bond. So the negative charge and positive charge are attracted to each other to form a bond. This is an ionic bond because it is formed by 2 ions. Okay, notice that ionic bonds follow the octet rule. Lithium's valence orbital, which is now its first orbital, is full. Fluorine's valence orbital is also full, so they are both happy. In ionic bonding, alkali or alkaline earth metals, and again, it can be any of the metals that do this, but we really are focusing right now on those 2 left-hand side columns. Alkali or alkaline earth metals send an electron over to nonmetals. This makes the alkali alkaline earth positive and the nonmetal negative, so they attract each other. So there's the nonmetals over there, and there goes the electron. So we remember that the elements on the left-hand side are the weak guys because they don't have strong pull on their electrons. They easily give up their electrons. And the elements on the right side are the strong guys. So let's compare the kind of structure that covalent bonds and ionic bonds make. Covalent bonds form molecules. So that's an H2O or water molecule, for example. It's a separate structure from all other water molecules. In other words, when you boil water, you have a bunch of water molecules together in your liquid water. And when you boil it, one water molecule goes flying up into the air in steam in one direction. Another one could go in a completely different direction. They're like cars. You can drive them in different directions. Ionic bonds don't form independent structures. They form what are called crystal lattice structures. So think of a lattice structure like bricks in a wall. Now, in this example, we're using sodium chloride, and that's table salt. That's one of the more common ionic bonds that we're going to talk about. It's one sodium and one chlorine. So no sodium belongs to any one chlorine. So if you pick any of those sodium atoms, particularly the ones in the middle, they're surrounded by 4 chlorine atoms. Actually more than that, but for this two-dimensional representation, it's 4. So you say, well, which of those chlorines does the sodium belong to? It doesn't belong to any particular chlorine. It's attached to all of them like bricks in a wall. Another analogy I use is apartment buildings. It's apartments in a large apartment building. You can tell each of the independent apartments from one another, but they're not separate structures. You can't simply rip an apartment out of an apartment building. It's not an independent structure. It's part of the overall building. Whereas again, molecules, which are formed by covalent bonds, ionic bonds do not form molecules. They are separate independent structures that can move and separate themselves from other molecules. We'll talk more about this concept. Finally, we're going to deal with the third type of bond, metallic bonds. We don't deal with this a lot in AP chemistry, but we will some. So the metallic bonds are between two metals. So copper, with the abbreviation Cu, easily passes electrons from one copper atom to another. So these are bonds between different copper atoms in say, a copper wire. In a metallic bond, electrons are attracted to the protons in the nucleus, but the electrons are not held closely. In metals, they have a large number of orbitals, usually 4 or more, and therefore the valence electrons are not held very tightly. So what they do is the electrons are not held closely to any particular atom, so they jump from one atom to the next. They literally just move around kind of freely in between copper atoms. So it's like a community of shared valence electrons. No valence electron belongs to any specific atom. It keeps jumping from one atom to the next to the next. And this movement of electrons around metal atoms is called the electron sea model, because it's basically like fish swimming in the sea. They can go anywhere they want in the sea of copper atoms and just keep swimming around up and down between all of the copper atoms. And that's really all we're going to say about metallic bonds at this time. So here's a comparison of how the bonds compare. So just keep these keywords in mind. Covalent bonds are atoms that share electrons. Ionic bonds, it's an atom passes electrons to another atom, and that positive negative ion then stick together because they have opposite charges. And metallic bonds, I don't know how well this analogy works for you, but electrons jump from atom to atom like frogs on lily pads. They can jump all over the place, freely moving from one place to the other around the atoms of the metal. Now here are some characteristics particularly of ionic and covalent bonds. So the unit of a covalent bond is called a molecule. It's a separate independent structure. The unit of an ionic bond is called a formula unit. So when we talked about sodium chloride a couple slides back, that's the formula unit for an ionic bond, sodium chloride. But remember, we said very clearly that a sodium chloride unit is not an independent structure. It's like an apartment. You can't rip it out of the apartment building, or it's like a brick in a brick wall. You can't rip a brick out of the brick wall. So it's a unit of the crystal lattice structure, which is the overall structure of ionic bonds, but it's not a separate unit. It can't move freely. Bond formation, ionic pass electrons, covalent share electrons. The elements involved for ionic bonds, it's a metal and a nonmetal. And for covalent bonds, it's 2 nonmetals or more, two or more nonmetals. The physical state, ionic bonds are always solids. However, covalent bonds can either be solids, liquids, or gases. I'm going to assume you have some sense of the meaning of those words. We will formally define them at a later time, but it's basically your table is a solid, the water that comes out of the faucet is a liquid, and the air that we breathe is a gas. Gas, by the way, doesn't have anything to do with gasoline that people put in their car. That's just a name for that particular chemical compound. Gas means the unattached molecules that are floating around like air floats around. Melting point. So ionic compounds generally have high melting points, whereas covalent compounds have lower melting points. Solubility in water, that means it dissolves. You all know that when you put salt in water, it dissolves. When you put a covalent bond like sugar in water, it breaks into separate sugar molecules, but the sugar molecules don't break up. You just get a lot of independent sugar molecules. Whereas salt, the formula unit, the sodium chloride, actually breaks into a sodium ion and a chlorine ion. That sodium and chlorine ionic bond breaks apart. That might not quite make sense at this point, but believe me, we'll talk about it. It will make sense. And then conductivity, that is how much does it carry electricity. Ionic bonds, a compound is very, very good. Now, you can't put electricity through salt in your salt shaker, but if you dissolve the salt in water, and we're going to do this, you can see that it can conduct electricity. Covalent bonds, like sugar, do not conduct electricity very well at all. Okay, so summary of covalent bonds, and I want you to really memorize this, and I'd like you to put this in your notes. I'm not going to give you an assignment sheet tonight, but I'd like you to write this in your notes and basically memorize it. So, number one, all atoms want to fill their valence orbitals. So oxygen agrees to share one of its unpaired electrons with hydrogen if hydrogen shares its electron with oxygen. Oxygen repeats this process with another hydrogen. Both hydrogens and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form separate independent structures called molecules. So there's the shared electrons. Okay, summary of ionic bonds. Ionic bonds happen between a metal and a nonmetal. So one, the high electronegativity of a nonmetal pulls on the electron of a metal. Two, the low ionization energy of a metal means that it easily gives up electrons. Three, the metal loses electrons and becomes a positive cation. Four, the electrons are passed across the periodic table figuratively from left to right across the periodic table. So five, the nonmetal gains electrons and becomes an anion. And finally, six, the cation and anion, positive, negative, are attracted to each other to form an ionic bond. Okay, so that wraps up the lesson. You learned basically how the only ways that atoms in the universe bond together to form compounds or form all the different substances. You learn that in less than 30 minutes. We're going to talk about it in a lot more detail. Of course, there's a lot of details to go along with this. I'm not going to give you an assignment for tonight. I would like you actually to watch this video twice and be sure you really understand this and you can really describe ionic and covalent bonds. And tomorrow we'll talk about it a little more and get into our first lab in class tomorrow. So have a great evening.